Good evening, everyone. Hello. Am I audible? Am I audible?
Yes, sir. Yes, sir.
Okay, great. Okay. So, how are you, all of you?
Fine, sir.
How was your quiz too? Is it good?
Good, sir. It
Okay.
was.
Was the questions easy?
Yeah, yes, sir.
Okay, great. Okay. So today basically we are going to discuss week 10. Uh, Hopefully week 9 has been discussed completely earlier weeks. Uh, So let me start with asking a question to some of you. I mean, when we are dealing with multivariable calculus, uh, can you point out some specific, changes from one variable calculus? I mean, what are the things we need to keep in mind for multivariable calculus? Can some of you just pitch in? What do you think? What are the important aspect of multivariable calculus, which was not there in one variable?
Good evening.
Yeah, good evening. Yeah, so is my question clear? I mean, what I am asking? This is not a particular, the question, but I want to know what do you think about this? What is the, what are the main differences of multivariable calculus from one variable? What are the main things which we have to keep in mind regarding this? Have you thought of that in week
In
9?
case of
Sir, I just joined now.
Okay. Yeah, we have just started now. No issue. Yeah.
Actually, sir, I have a few doubts in concept related to concept.
Where?
Sir, I don't understand what is A tilde and open wall around it, and what is this concept of
Okay.
is A tilde a
Okay.
point, and why do we take open wall around it, and how is it related to all the derivatives and tangents?
Okay. So yeah, we will
Actually, I know
discuss
the
this.
concept, sir. I know the concept. I know the formula. I know how to apply them, all that.
Mm-hmm.
But I
Mm-hmm.
cannot visualize it.
Yeah, yeah, right. I got your point. Right. Yeah, we will definitely discuss this. But let's start with what I am asking. I mean, I want to know what you think about this.
About what,
Anyone?
sir?
in may I say
Yeah, can you speak little bit louder? I cannot hear you properly.
uh, am I audible?
Yeah.
Uh, Actually, in case of a single variable, when
Hmm.
we define the limit, we are approaching from the left hand side and from the right hand side. These are the two ways from which we are approaching to a point.
Good
Whereas
evening, sir.
in case
Yeah.
of
Good evening.
multidimensional,
Hmm.
you can approach to a vector from any
Hmm.
direction.
Yeah. Right. This is one very important thing we are dealing here, right? Yeah. Any other point which comes to your mind? Uh, just now, someone has asked about open ball. So, have we came across open ball in one variable calculus?
Also, I don't know, sir. I asked the question, but
Yeah, yeah.
that's what.
But can you identify open ball with? Is this analogous to something which you know in one variable?
Sir, I studied a concept of locus. Is it something related to that?
Not Lucas. Lucas is something different. That is not Lucas. Uh, okay. Anyone wants? So that is my second question. So you have heard open wall has came in many places in multivariable. Have you seen anything analogous to open wall which we have came across in one variable?
Points, nearby points along the line in one variable.
So we call it neighborhood, right?
Neighborhood. Yes.
But when we talk about neighborhood, do you use any other term for that? Do you remember?
That is limit, I think.
Huh?
Limit.
No, limit is in both place. I mean, it is same for multivariable and one variable. That is okay. Okay, fine. So I am starting from a little bit from week 9. Is that okay? I mean, I want to discuss some
That will be
concept there.
better, sir.
Yes, sir. Yes, great.
Yes, sir.
It
Okay.
Yes,
will be
sir.
better.
That will be
Okay.
better for sure.
Okay, fine. So let me share my screen
Yes, sir.
first.
Because of quiz 2, we haven't focused much on week 9. So, yeah.
Yeah, that I know. And this is a new concept of multivariable, so I think we can
True.
start from here. So
Yes, sir. Thank you, sir.
yeah. And I have not taken any live session in quiz 2, right?
Yes, we missed you, sir.
So actually, I was
Oh, sir, you
already
have week 5, I guess.
week 5. Yeah, till week
Yeah.
5 we have. Okay, fine.
Because I remember that, sir.
Yeah.
Only. Yeah.
So when we are talking about multivariable calculus, there are more than one variable, that is quite clear. Now, say, let's start with the limit concept. Someone has already pointed it out. So what we have done here, so this is the x-axis and this is y-axis. Basically, here we point the variable x, and at this direction we have our fx, right? Suppose our function is like this, something like this, and we want to find limit at x equal to a, right? So what we have learned there, we can approach x equal to a from left side and right side, right? Only two directions are available. No other directions are available, right? Because this is only the variable set we know, and that is a, if you, now you know what is dimension in terms of vector space, right? So that is basically one dimension thing, right? The straight line. So only two directions are there, from left or from right. And when we are talking about the neighborhood of it, so this is the neighborhood of it, some neighborhood, a plus some, let me call it h, and this is a minus h, right? That we have learned. So if I write it down, this is my neighborhood of a, right? Neighborhood of point A. Now what is it called? This is open interval. You know what open interval is, right?
Yes, yes, yes.
So this we have learned in Maths 1, first week, what an open interval is. So if we want to write it as a set, what we know? What are the points will be there? So this is all x belongs to real number such that this condition satisfies, right? We don't take the boundary points, correct? That's why it is open. Okay.
Yes, sir.
So now if we want to generalize this in multivariable calculus, let's see how it happens. Now we have, suppose we are doing it two variable. It is easy to visualize, so let's do it in two variable. The same concept we are basically trying to see. Now two variables, suppose this is my x-axis, this is my y-axis. So let me write it as small x and small y as our variable like this. And along z-axis, we write fxy, right? So this is along z-axis. Okay, so our variables are two, x and y. These are my variable. And along z-axis, we are writing down the values of the function. depending on x and y, correct? The same thing we are doing in one variable. Our only variable was x, and we are writing the values along the other axis. So here we take another axis, that is z. So here when we when we draw the graph of the function, what we will get? We will get something like a surface, correct? In general, it may be different, but in general, we will get something like this, right? For different value of x and y, we will get a point here. So it will be like a surface. Okay, fine. Till now, this is okay.
Yes, sir.
Okay. Now, if we take a point a comma b, and we want to find the limit of the function at that point. So this was basically limit x tending to a f of x. Now we are concerned about limit f of x comma y, where x comma y tends to a comma b. So now we have to approach a comma b and see how the functional value changes. That is the approach we know to find the limit. That is basically the definition. So this is what it looked like geometrically. Now, how many ways you can approach to a comma b? There are infinitely many ways, right? There are infinitely many ways we can approach a comma b, right? So, infinitely many ways, what does that mean? So let me clarify it a little bit. Suppose I have a comma b. So we can take straight line passing through a comma b. So there are already infinitely many straight line. And we can take any curve also, right? We may not want to see how we approach using a straight line. It may be a curve like this. And so there are infinitely many pattern of curves, infinitely many equation of curves which passing through a comma b. So not only the straight line, it can be curve also. It can be parabola passing through a comma b, it can be hyperbola passing through a comma b, anything, any curve, any arbitrary curve, even we don't know the name of the curves. That can also be the part of this journey. Okay? So there are infinitely many ways, that for sure. It can be straight line, it can be a part of parabola, anything. So when we approach a comma b, what are how the functional value changes, and we will find out the limit in that way. That we already know how to find the limit. Now, what about the neighborhood of a comma b now in this case? If we can apply the same concept from one variable, what we will get here? So if we consider a neighborhood, it will be something like this.
Circle.
Right. You have said circle. Who has said that? Can I know your
Sir.
name?
Nikhil.
Nikhil. So Nikhil has said circle. So my point is the neighborhood only be a circle?
No, sir. It will be a disk, right?
Yeah, it's a
In
disk or
two
circle,
variables, it will
anything
be
that is
circle.
okay. But it is a disk, right? It is not a circle because neighborhood means what is in between that point and that
Plane.
boundary, right? It is a disk. But I mean, is it only a circular thing? I mean, is this necessary? No, right?
Yeah. It
In
can
case
be
of
any.
one variable, there is only one possibility, which is on the straight line. There is no other possibility. But here, we can take anything, right? We can take, this is also a neighborhood, which is not a circle, triangular shape. This is also a neighborhood. Anything which is square shape or rectangular shape, anything is possible here, right?
Yes.
Right. So neighborhood of a comma b means there can be infinitely many possibilities again in this multivariable calculus. But to take a standard thing, we are considering a disk, which is basically called open ball. Now for two variable, it is a disk. Now when we go to three variable, it will become a sphere,
One more.
right? For three variable, we know it's a sphere. Now, what about four variable? When you go to four variable, more than three variable, we don't have a name there, right? That's why we call a n ball. depending on the dimension. Okay, that is the open wall. Open, why it is open? Because we don't consider the boundary, because we don't need that. What happens in the boundary, we only need what happens in between. That is enough. So that's why in one variable we consider open interval. In two variable we consider it a open disk. So for two variable it is open disk. So if I write in a set form, I will get x square plus y square, not x square plus y square. So this is a comma b, right? So x minus a whole square plus y minus b whole square less than some radius r. Correct? That is our equation of open disk. And in three variable, it will be open sphere. And above the three variable, we can call it n ball depending on the dimension. So n is the number of variables in which we are talking about. Okay. So is this part clear?
Yes, sir.
Okay. So
Sir, can I
basically,
ask
open, yeah.
one short question? So why it would be x minus a square?
That was the equation of the circle, right? This point is a comma b. So circle centering at a comma b is with radius r. The equation is x minus a whole square plus y minus b whole square equal to r
Okay.
square, right?
Okay, sir.
I mean, that was in class 11 or maybe 12, I don't know, I forget that.
Okay.
But these are the equations of circle, right? So all those points which is less than this, less than r square, that will be inside the circle. Okay. Okay. So till this portion it is clear. Okay. Now the same type of question will arise that in one variable calculus we have seen some cases where limit does not exist. Correct?
Yes, sir.
Can you give some example? Any one example?
Sir, 1 by x.
Function not continuous at that point.
1 by s is okay. At 0, limit does not exist. But any other example you remember?
Mod of x.
Huh?
Mod of x at 0.
Mod of x at 0. Limit does
Sir,
not exist.
x square by y cube.
The step function.
Limit doesn't.
Step function is a good example. But some of one of you have said mod of x.
So no, it's not continuous. Limit exists.
It is continuous.
Yes,
Mod
sir,
of x.
it is continuous.
It is not differentiable.
Yeah.
It's not differentiable.
So limit exists and it is continuous because it will look like this, right?
Yes,
okay,
sir.
so let consider mod of x. What is happening here? So when we are approaching from the right side to 0, from this side we are getting towards 0, and when we are approaching from the left side, from this side we are getting towards 0. So from both sides we are getting towards 0, so it matches, so limit exists, right? That was the concept. If it does not match, suppose I am taking a function, I am defining a function like this. Someone has said step function, that is also okay. Now, if we define a function, suppose if x is x plus 2, when x is greater than 0, greater than equal to 0, maybe, and x minus 2, when x is strictly less than 0. So what happens for this case? Limit extends to 0. Is it exist?
No.
Okay. How we can show it? Same thing. When we are approaching from the right side, what will be the limit?
2.
When we are approaching from the left side, what will be the limit?
Minus 2.
Minus 2. So it does not match, so limit does not exist, right? Okay. So in this case, this is quite easy, right? Because we have only two ways to check it. Now, what happened here? So suppose I am taking a function fxy. So this is a famous example basically. xy by x square plus y square. So, and we want to check limit of xy tending to 0 comma 0, does limit exist?
Sir, it would not exist.
Why?
Reason, put a line, so take it on along the line y equal to mx. Put y equal to mx. So all the variables cancel out. That means x eliminates and only the constants remain. That means it does not depend upon the constants. It cannot depend upon the constants.
Why?
There is no way. So all the variables are eliminated.
So ultimately we get some constant, but why that is the proof that limit does not exist? You are right, but I want to go a little bit deeper. Why?
Sir, for the different value of the constant, the value of the limit will change.
Exactly. And what does it suggest?
Basically, it has different limits.
Yeah, right. So basically, if we take different state line, we'll get different limit, correct? So we are considering, so again, we go back to this point where we are saying that there are many curves approaching to AB. So here my point is 0 comma 0. Now we are approaching 0 comma 0 via different straight line, right? So this is a straight line passing through 0 comma 0, correct? So if I approach to 0 comma 0 via this straight line, what will be the functional limiting value when we are approaching to by this point? So in this case, y equal to x means x square by 2x square. So it's half, right? Correct? Now if we approach via y equal to 2x, what will be the case? It is 2x square by x square plus 4x square, I think, no? So 2 by 5. Correct? So you can see we check only two straight line and we are getting two different values. Correct? But if limit exists, then it should be unique via all the points, via all the curves in this case. But this does not happening here, right? So limit does not exist. We can conclude from here. So here, basically our aim is to find two different curves, at least two different curves, via which the limiting value will be different. Then we can conclude that limit does not exist. Is it clear? But in the other hand, when limit exists, I mean, it does not guarantee that only via straight line the value is same. It does not guarantee that limit exists in that case, right? Because there can be some other curves via which limiting value may be different. Clear?
Sir, may I ask you one short question? So
Yeah.
limit, what does it mean that limit does not exist? This means that we cannot reach that point via that code.
No, limit does not exist means if we approach the point 0 comma 0 or some other point a comma b via different curves, we will get to the same functional value. Okay, the function will approach to the same point. If that happens, then limit exists. Otherwise, it does not.
Okay. Means that via different points we are reaching by different curves.
Curves, we are reaching different values via function. That means limit does not exist.
Thanks.
Okay, so this is a good point to show some visualization, maybe. 1 minute. Something should come here. Can you see this screen? Is it visible to everyone?
Yes, sir.
Yes, sir.
So I am taking the same function xy by x square plus y square, right? You can see this is the surface which we are talking about. Okay, x square plus y square. Sorry, xy by x square plus y square. So this red axis basically x-axis, green one is basically your y-axis, and the blue one, which is perpendicular, basically z-axis, where we are plotting the function. Okay, so we are taking different straight line, okay, and see what happens to the functional value at the zero, at the point zero. Okay, so if we change this m y equal to mx, if we change the m,
So
the
at point zero means that the point 0, 0.
0 0 origin. Okay, so basically what we have done, we are seeing this now visually. Okay, at the point 0 0, what is happening here? So if we change this m, this is the equation y equal to mx. So basically I am showing this programming also so that you can do it on your own. That will be great. So y equal to mx is your straight line, and if I change my m value, the straight line will change, right? The slope of the straight line will change, so we will get different straight line. And the black line which you are seeing, that is basically the intersection of the straight line with the function. Okay, so this now in 3D y equal to mx will be a plane, not only a straight line, correct? And when the straight line we are seeing is basically the intersection of that plane with the function. Is that part clear?
Yes,
Sir,
sir.
this means that the plane consists of all those straight lines which would intersect this graph at different values of m.
So in 3D, in three dimension, in R3, okay, in R3, if you write mx comma y, okay, comma z, now how many free variables are there?
2.
Two. That will be a two-dimensional thing. That will be a plane, right?
Yes, sir.
We have seen in linear algebra. So this is x comma mx comma z. So
So
x
I
is your
can
free variable.
suppose I have to visualize it. Suppose
Huh.
I am this green plane is visible to me, right? I
Huh.
place the line on top of it, and I drop the line, right? It would cut through all these points. It would cut the curve at all the points where the plane is intersecting the graph.
Exactly. Right. So suppose let's see only the plane first. If we write y equal to mx, okay, y equal to mx in R3. So that will be your plane, correct? Why that will be a plane? Just now I have explained. That is basically set of all points as that x comma mx comma z. X comma y comma z. Now y is dependent on x by this equation y equal to mx. So it will be a two-dimensional thing. That will be a plane. So when I am writing y equal to mx, I will get a plane, right? Now I want, and why we are taking y equal to mx? Because 0 0 should lie on there, because we eventually we are going to approach 0 0 via different straight line, correct? That is our aim in this case. Now we are introducing this function. So that will be a surface. So it will intersect this plane, a particular y equal to mx. So here m is minus 0.3. Now what we are seeing. So it will intersect the functional values, intersect this surface. Now at how many points it will intersect? I mean, the set of points where it will intersect, it will be a straight line, right? It will be a one-dimensional thing, correct? So if I take this intersection path p comma a, so a is our function and p is the notation for the plane I have given. So if I take the intersection of both of these two, we are getting this straight line, this black line which we are seeing, correct? So now I remove this plane, so I am getting only this straight line. Okay. So via this straight line, what we are getting basically? Can someone say what this straight line basically representing here? This is easy. I mean, what this straight line represents there?
Is it
Anyone?
tangent to the surface?
No, we are not doing to
Variables
tangent
x, y.
now. So what I have said, so let me go back to this, then I will come back here again. So basically what I was saying, y equal to mx I have taken, this is a plane, and my function was fxy,
Your
xy by,
screen is not visible
oh, is
if
it?
you're writing something.
1 minute. Yeah,
Yeah.
now is it visible?
Now it is.
Yeah.
Now it is.
So basically this is the plane and this is the function. So this function, the surface is the basically representation, graphical representation of this function, and the plane was basically the representation of this y equal to mx, right? And when the straight line represents the intersection of these two, what does it mean? We are basically replacing y by mx, right? That is what we are getting.
Limit.
Intersection of these two, correct?
Function in restricted set of domain.
Basically we are substituting the values y equal to mx. So when we are substituting, we are getting, so this is m square by square by what we have done earlier. This is exactly what we are getting here, right? So it will depend on only on m. So this is what we are seeing here in this case, right? Now if we change the value m, we can see this value changes, right? At different point, this value changes, correct? Is this okay? Now if we are approaching,
Sir, when we're changing M, does that
hmm.
change the plane or it remains the XY plane only?
No, it will, the plane will be changing, no? You can see the plane is moving, right?
Okay, so the plane changes.
Plane changes. That's why the straight line changes, right? That's why the straight line
It's still
changes.
the XY
Sir,
plane, but then it is just rotating.
It
at
is
this
not
point,
xy plane.
it
It
seems
is
that
y
Sorry?
equal to mx plane.
Okay.
It is not xy plane. It is the plane like this. So x, mx, z. This plane. This is a plane, right? This plane. Y equal to mx means this plane.
So every time we change M, it becomes a different plane.
Different plane, right? So the setup point will become different.
Basically,
I
it
don't
will
understand
rotate
why.
along y and z axis.
Huh?
I don't understand, sir. Why
Basically, it
put
will.
that in a straight lines?
Which one? No, we are just seeing the intersection. That's why it is becoming a straight line. A plane which is cutting the fxy, we are seeing where are the points where it is cutting, basically. Okay?
Yes.
Okay, fine. So basically my point is here, when we are changing the m, we are getting different plane, and if you see around 0, if you see around 0, yeah, here. So this is the origin, right? At the intersection of this red and green line. This is the origin, right? So along that point, if you see along the z-axis where the functional value are representing, so you can see this is not fixed, it is moving, right? If limit exists, it should not move. It should be a particular point, right?
Yes, sir.
So if we change this function now, suppose if we change this function. What should I write? This is a good example. We can stretch it out. So this is the function x square plus y square, right? Again, we are seeing y equal to mx, this plane. So as you can see, the intersection will represent the intersection of the plane and the function on this
Function.
surface x square, that will be like a parabola basically in this case, right?
Yes.
Okay.
Sir,
Now
can
if
you
we change this,
sir, yeah, that's what I was saying. Sir, can you vary m so that we can visualize?
So if we change this m, you can see the plane is moving, so the curve is moving, right? The curve is moving, and this curve is passing through the origin, as you can see, because our plane is passing through the origin. Our function is also, there is a point, function of value at origin, which is 0 eventually. And you can see at 0, 0, this value is always fixed. It is not moving, it is not changing, right? But that was not happening in the earlier case, correct? So in this
Yes.
case, I mean, this is not the proof why the limit exists, because we are only considering straight line. But in this case, we can see for all the curves when we are approaching the origin via straight line. So this is the straight line by which we are approaching the origin, y equal to mx, where it intersects with xy plane. That is the straight line I am talking about. Okay. So if that straight line changes, still the functional value, where it approaches at 0, 0, it remains fixed in this case, which was not in the earlier case. Correct?
Yes.
So the
May I
difference
ask-
is clear?
Yes, sir. Can we say that the function has to be symmetric for it to
There is
be?
no particular way we can conclude anything in this case. That is the point. Okay. We
May
have
I ask a
always
question here?
approached different way for different problems. There is no other way.
Okay.
Yeah.
Yeah, my question is, okay, understand when you say y is equal to mx, we are having this. But if the line approaches y as z, because this is a three-dimensional surface, if the line approaches y as z, like then how do we actually go about? Because then it will be the plane itself.
No,
will be
we
different.
cannot take line via z. The line always should be on xy plane, because that is your domain.
Okay.
Right? So yeah, that is what I have started with at the beginning. We are approaching via the points inside the domain, right?
Okay. Okay.
That was for one variable, that was for two variables. So it is always from the domain. Right?
Okay.
We are concerned about that. Yeah. So the curve we will take should lie inside the domain, right? And then we'll see how the functional value changes depending on those curves. Is it clear?
Yes, sir.
Yes, sir. When, sir, three-dimensional, then three
Then it
values.
will be an open wall and basically open sphere, and then that will be a hyperplane in your surface which you are taking. And so that is, I mean, I cannot show here by anything because we cannot visualize 4D, I mean, whatever we have till now. But you have to visualize in your mind. That's how it's working. Right? So geometry we can see till 3 dimension, and that is why when we are talking about two variable calculus, we can see the geometry clearly. Otherwise, you have to do the math. Okay?
Yes, sir.
Yeah.
Sir, curve lies inside the domain. What is
So we are
yeah.
approaching this point a comma b, right? When we are talking about limit xy approaching to a comma b.
Okay.
So whatever curve we are taking, whatever straight lines we are taking, that should be passing through A comma B, and that should be on your XY plane, right? Because this is your domain,
Okay.
right?
Okay.
Yeah. So suppose in this picture, I am taking this curve which I have shown here, this curve. Now, if I consider this thing, the functional value will change like this, correct? Here, and it will approach to this point. That is what I was showing in the GeoGebra. That is exactly what I was showing. Okay. So
Yes.
let me draw it little bit more clearly here once. So suppose this is my surface. Here is the point A comma B. Okay, I am approaching A comma B via this curve. Okay, this may be a straight line, may not be a straight line. Okay, so what I have done here, I have taken a plane containing this curve for visualization. Okay, and this plane will intersect somewhere here, this surface. So that's how this curve, what this curve represent. So let me draw it in other color.
Yeah, this is the intersection. Suppose we raise this line in XY plane and take
Exactly.
it,
So
it would pass through, drilling a hole in of this kind.
right. So
But sir, this is
suppose
not a
at this
straight line.
point, this is the functional value. So if I take this point, this is inside the domain, this is the functional value. This is the point in domain, this is the functional value, right? So we are approaching A comma B by this curve, and that's how the functional value is approaching here. And this is the limit, if it exists. Okay, correct? It is clear. Now suppose
Yes, sir.
limit does not exist. Suppose for this function, limit does not
May I
exist
ask one
somehow.
question? May I ask a question
1
before
minute,
you?
let me finish this,
Okay.
then I will
Okay.
take your question.
Sure, please.
Yeah. So basically what I was saying, that suppose there are some other curve. This is another curve. Okay. So here I am getting another curve like this, which is basically the functional value depending on these points on the curve. Now, suppose this does not approaching to the same point. This is approaching here, which was happening in our case xy by x square plus y square in case of origin, right? So here it is approaching here. It is approaching here. So these 2 points are different. So we can say limit does not exist. Okay, because we are approaching to the same point A comma B, but we took 2 different paths. And when we are seeing the functional values, we are saying that their functional values are approaching to 2 different values. That means limit does not exist. If limit exists, you can take any path, the functional value should be approaching to a particular point, to a unique point. Clear?
Yes.
Yes, sir.
Yes, sir. Yes.
Okay. Yeah. Now you can ask your
Yeah.
question. What was your question?
Is that a projection that we are always doing in
Yes,
terms
sir.
of finding a limit?
Is it a
You can think it as a projection. You can think it as a projection.
orthogonal
But
projection?
it is kind of inverse of a projection, no? We are taking
Yeah,
something in xy plane and take the
okay, we keep
projection
the
on
light
the
source
fxy.
below the XY plane and
Ah,
look at the shadow.
maybe you can think like that. So it depends how we are visualizing it. Okay. Yeah, it is actually a projection, but why I was saying inverse, like because the above thing is not a vector space, right?
It's going from
Because
R2 to R3.
Which one is not vector space, please? The surface, you mean?
I mean, this surface,
Okay.
this may not be a vector space, right?
Yeah.
It may be, but it may not be also. Because first of all, what the picture I have drawn 0, 0 is not there. Correct?
True. Yeah.
Yes.
Yeah.
And it is also not, I mean, if it is a vector space in 3D, it should be a plane or straight line. It is neither of that.
Okay, so now about the concept
That's
of
why I did not use the word projection.
Okay. Okay.
Because projection we have seen always should be on some subspace, right?
Correct.
Yeah. Yeah, but it is analogous to that.
Okay. Okay.
Yeah. So at least the concept of limit is clear,
yes.
more or less.
Yes, sir. Yes. Now it's clear.
Very clear.
Fine. So this is what I wanted to tell for the week 9 thing. And okay, so another thing we have seen in week 9 was directional derivative, right? Which eventually connect with week 10.
Yes, sir.
So let's come to directional derivative.
Sir, can you mute everyone?
Yes, sir.
Okay, fine. Okay, so directional derivative. Can someone tell me what do you understand by directional derivative? Just a discussion. I mean, we are doing an open session.
I know it theoretically. Rate of change in the direction of unit vector, a particular unit vector.
In one
particular
variable.
unit vector in that direction, right?
Rate of change of a single variable.
No, that is partial derivative.
Okay.
Right.
Slope in a certain direction.
So rate of change in a particular direction at a point.
Correct. Yeah. So more or less whatever you have said is correct. But why have not we considered it in case of one variable? Now you should answer this because we have discussed the limit thing. Why we have not considered directional derivative in case of one variable?
There is only.
Sir, in one variable there is only one
two directions.
Either two direction. Either we can approach it from the left or we can approach it from the right.
So in one variable, what does this derivative represent basically? Suppose I want to find the derivative of this function at this point. What does it mean?
Sir, rate of change of the rate of change of output of this function with respect to variation in x coordinate.
Sir, a tangent at that point.
The tangent will be in a same direction. If in a one-dimensional space, the tangent will show the only single direction.
Right, correct. So their direction was not an issue in that case, right? Direction was not an issue in one-dimensional case because rate of change means what? If we take the neighborhood of it, that's how it is changing. So direction was not an issue in case of one dimension. Now, in case of two variable, what is happening? Suppose I have a function like this. Okay. Similar type of function I try to. Now, this is the point a comma b where I want to find the derivative. Now, here you can see, if we take the neighborhood of it, this is the neighborhood of it, the functional values of the neighborhood. Okay. Now, there are infinitely many directions coming in the picture. In which direction are we talking about? Right? The rate of change. Correct? Do you understand the difference?
Yes, sir.
That's why directional derivative is important.
Yes.
So we should mention, when we are asking about the derivative of a function, in one variable, it is enough to indicate the point at which point I was talking about. So in case of this, the x equal to a, that is enough. Now, in case of two variable function, we should indicate the point also we should indicate some direction, some vector along which we are trying to find the directional derivative. Correct? So that vector is important here. Now, if the vector is unit vector along the variable, I mean along x-axis, if we consider the unit vector, so this vector in this case, so let me erase this. So this is my a comma b. So if we consider the unit vector, this is 1 comma 0, right? So this direction basically we transcend this at this point. So this along this direction, if we consider the rate of change, what is it called? This is partial derivative with respect to x. Correct? If we take this direction 0 comma 1, we transcend this along this, and if we consider the rate of change along this direction at that point, that is partial derivative with respect to y. Right? So partial derivative is a special type of directional derivative. Correct?
Why do we always take the unit vector? What difference does it make if we don't take a unit vector?
First of all, the one thing I can say, this is one convention. We are always dealing with unit vector. And second thing is, I mean, we don't have to worry about the norm of the vector, the length. We don't have to worry about that, right? Because unit vector means norm is 1.
Yeah.
Right? And if we know the rate of change along that unit vector, we know the rate of change along any vector in that direction.
Yeah.
Because that is the scalar multiple of that.
Yeah, yeah.
Correct? That's why we consider unit vector as our convention. Okay? Is it clear?
Right. Yeah, yeah. Thank you, sir.
Okay. Okay, great. So this part is at least geometrically we can visualize what is happening here, right? Now, if we consider suppose 1 comma 1, we transcend it here and we will calculate the rate of change, right? Clear? This part is clear. Now, can someone tell me how we calculated the D?
Sir, the easiest way is to calculate the gradient function and give it a dot product with this unit vector.
That is the formula which sir has taught in one lecture. But what is the definition? First, let me.
Rate of change, suppose we are taking it with respect to x. It is the rate of change along x-axis. If we take it along y-axis, then it is the rate of change along y-axis. We have to consider the rate of change in particular direction actually. It may be x-axis, it may be y-axis, or it may be any other direction.
But I was asking about the limit definition. So, okay, you have said, right? Suppose you are saying this. So I should write a comma b here. Suppose partial derivative a comma b. So what is the definition here?
Limit h approaches x comma 0.
A plus h.
X plus h. A plus h.
Limit h approaches x comma 0.
Not x comma 0. Right? This is what we are talking about, right?
Yes, sir. Yes.
This part is quite clear, right? Why we are taking this definition.
Yes.
This is kind of, we are considering it in one variable. Our second variable is fixed. We are talking about only one variable. That is if a plus h minus f of a. Right? The second variable is kind of fixed. But here we have to consider the functional value along that point also. That's why we are taken b. Correct?
Yes.
Clear? Now, if we consider it in terms of any other unit vector. So this is basically along the unit vector 1 comma 0. Now we take some other unit vector. What should be the definition?
Limit s tends to 0.
A comma h, a plus h, comma b plus h.
Yeah, someone was saying. Yeah, go ahead.
A plus hu, function a plus hu minus f.
B plus hu.
B plus H
B plus HU
minus
minus
F of A comma B
Comma B upon
divided
A.
by H into U.
Correct. Correct. So this U means we should consider U as U1, U2.
U2.
So I should write here U1 and U2. Correct.
Yes.
Now what I have said for 1 comma 0, is it the same thing what I have written here? Let's check that.
Yes.
So U1 is 1 and U2 is 0. So we'll get back to here. Now, if we take U1 as 0 and U2 as 1, we'll get back to the fx, fy, maybe.
F of A
F of A
comma B plus H
comma B plus H
minus F comma minus F of A comma B by H.
Correct. So whatever we have understood from the above geometrical representation, it is basically the same thing. Correct. So that's how basically directional derivative work. We can directly calculate it from the definition, or the other way where we consider the gradient and take the dot product with the unit vector.
But so while taking the gradient, we have to check the continuity. It is only
so this formula, that's what I was going to tell. This formula only valid for the continuous functions, right? I mean, the gradient should be continuous, not continuous function. The gradient should be continuous. Otherwise, it is not valid. Okay, but this definition always holds because this is the definition. That's why it is the definition. So yeah, this is always a good thing to visualize or remember. Okay, now if I try to see this in GeoGebra, yeah. Okay, let's see. Yeah, can everyone see my GeoGebra screen?
Yes, sir.
Yes, sir.
Okay. So here the function we have considered it x square plus y square by 2. Any function you can put here. So this is basically an applet. Here you can change, you can write anything you want. You can change this. Okay. And this is inbuilt basically. Okay. So we consider a point P. P is 1, 1 here. You can see the point P. I am indicating with the cursor. This is my point P.
Yes, sir.
Okay. And the unit vector, so I am taking a vector. This is basically making 45-degree angle with x-axis or y-axis from the both direction. So this is basically what should be this 0.71, 0.71, this vector we are talking about, which is making 45-degree angle. Correct?
Yes.
And we are trying to see how directional derivative basically is working, right? So this is the point P. We consider this unit vector. This is the unit vector we are talking about. We have normalized it. So this is the unit vector we are talking about. So along this direction, how the function value changes, we have calculated. So this is calculated here. It is 2.12. But that is not the main thing I want to say. I want to see if we change the unit vector, fix the point is always 1, 1, how the directional derivative is changing. Okay, so you can see how it is changing. So I am basically changing the vector. So if I change the vector, you can see the rate is changing. Rate of changing the function is basically changing, because so what here it is showing, along the unit vector we draw a plane. It is intersecting the surface of the functional values, which is creating a surface. It is intersecting that, and our point is fixed. But this straight line is basically showing the rate of change is basically changing because the slope of the straight line is changing. Okay, so here slope means what? So this U-type curve, is basically the
Slope.
intersection of the plane and the surface, right? And that straight line is basically tangent at that point. Now, if the slope of the tangent changes, that means the rate of the change of the function is changing. Otherwise, this slope should remain fixed, right? So If
Sir,
I
could you
change my
repeat the
vector,
last thing you just said?
So let's start from the beginning. We fix a point P 1, 1. First fix the point. Afterward, I will change the point also.
Is
First
P
fix
the
a point.
similar to what we were looking at A? P is similar to our A. We did
Which
F
was
of
our
A plus H. So P is
P
something
is
similar to
basically
A.
A comma B, A comma B, A comma B, right?
Okay.
P is A comma B. Okay, here it is 1 comma 1. A is 1, B is 1. Okay, and U is our vector along which we are considering the directional derivative. Okay, so if I change the vector, the plane which passing through this vector, and also the point, right? That will that will form a plane, and that plane intersect the surface, correct? And that will give me a curve, and this line is basically tangent to that curve at that point, right? Now the slope of the tangent will be basically the rate of change along that curve, right? So that basically indicate the rate of change of the function which we have started with at that point along this vector. Is it clear? I mean, there are many layers. I know it is difficult
Yes,
to
sir.
comprehend, but
You mean to say that this conical surface is a curve, right? And we have placed a unit vector at angle 70 degree with respect to say x-axis. It contains a plane, and this plane cuts this surface, conical surface. It forms a curve in two-dimensional.
Correct.
And this at point P, this line is a tangent to it.
Exactly. And the slope of the tangent is basically the directional derivative, the rate of change, correct?
In this red vector
at that point along this vector.
Yeah.
Sir, as we're changing U, this plane that we're intersecting this function with is changing, right?
Yeah, it will change, no? Because
So
what is this plane? This plane is basically passing through the point P along this vector. Now, if we change the vector, the plane will change. See?
Okay.
The plane
And
will
we're
change.
basically drawing the tangent at P on that curve of intersection between that function and that plane.
Exactly.
Is that
correct?
Right?
Yeah, exactly. And the slope of the tangent is your directional derivative.
Sir, one thing more. This point P acts like a hinge, right? And the plane is rotating on that hinge.
Exactly. You can think of that. Think like that. Yeah. Correct. So if I change the plane, you can see now the tangent is basically changing in other direction. So directional derivative become negative, right? So that's how it is working. Okay. So for a particular point, if we change the direction, change the vector, the unit vector, we'll get different directional derivative, right?
All along the
And
point on which the point on the surface remains the same. It's only the plane is rotating, that's all.
Exactly. Because we are changing only the vector, right?
Okay.
Yeah. Now, suppose I am fixing this vector, the vector I will not change again. I will change the point. Again, the plane will change, right? So it depends on both the point and the unit vector. And that's what we have seen in the definition, right? A plus H U1, B plus H U1. So it depends on A comma B and also U1 and U2. It depends on both, right? So if we change the point is changing, you can see, right? So the tangent will also change because the plane will change. And the plane will change means the curve which is intersecting with the surface will change. So the tangent at that point will change. Correct? Is it clear to everyone?
Yes, sir.
Clear? So now I think this is a great applet for directional derivative. I mean, if you can see it on your own, I think your visualization of directional derivative will not be a problem at any point. Correct? Is it clear? So if I change the point and fix the direction, fix the vector, the direction derivative will change. If we fix the point and change the vector, the direction derivative will change. If we change both, the direction derivative will obviously change. Okay? Clear?
Yeah.
Yes.
What would be a example for mentioning the relevance to this? Because, okay, if you're talking about, let's say, speed and velocity, and then you differentiate it, you actually get the distance. So like that, is there any particular example that we could probably from the subject that we're studying in vector spaces, or what would we do with this information? How would we
I mean, you don't have to think about any complicated physical example. I don't suggest that. See, you have some data, okay, which depend on two variables, right? Two different constraints, right? So you consider one as your x and another as your y, okay? Some x will affect your data, some y will affect your data. So what you are seeing superficially is basically affected by both x and y, right? Now, at some point, you want to know how this is changing, how the rate of what you are seeing, the result, how it is changing at some point, right? So there are many direction in which you can think it about, because eventually we are dealing with a multivariable function.
Okay.
Correct? So that is the significance. Now you can fit in any aspect you want.
Okay.
Correct?
Yeah, right.
Got it, no?
Yeah.
Okay, so
Sir,
I
have a
am...
question. Sir, I have a question.
Yeah, go
Earlier
ahead.
we were looking at the intersection between the function, I think xy upon x squared plus y squared with y is equal to mx, and we saw that the intersection was basically a straight line.
I mean, at all point it may not be a straight line, right? I mean, yeah, go ahead. What is the question? You finish it. Yeah.
So in such a case, how would we find the derivative? Because we saw whenever we hit such places in a single variable function, we are not able to get the tangent.
Where?
We are not able to find the derivative in one variable function.
Where limit does not exist, right?
Where limit does not exist, or there is no continuity.
So the same case will
Or
be
it's not
also here.
differentiable,
If it is
rather
not,
it's not differentiable. If it's not differentiable, so
it may be possible that direction derivative does not exist. It may be possible in here also.
Okay, so similarly it may not exist.
Yeah, same thing. That's why the second thing is very important. I mean, you have a formula, right? Gradient dot unit vector, right?
Yes.
Is equal to your directional derivative. Now, this gradient may not be continuous, then this formula does not apply. But even in that case, directional derivative may exist, then you have to check via definition. Now, in definition, if you check the limit does not exist, that can happen, right? We have seen such function, see some function where limit does not exist. If you come to a point where you can see the limit of the function in this definition, this one. If this limit does not exist, then directional derivative does not exist. It can happen.
Yes.
Right? Yeah.
Yes.
Okay. Fine. So
one small question I want to ask you. Sir, do we always have to, for continuity, do we always have to take 0.00 that h approaches to 0? It may be some else point, somewhere else.
Yeah, it can be some any other point. That's why I have said a comma b. I have not said 0, 0. So when I was talking about limit, I have said a comma b. Any point, right? At any point, we can ask about continuity or limit or differentiability, anything, right? It's for any point in the domain. Okay?
Yeah.
The origin of the unit vector will be on that point, sir. Origin of the unit vector will be the point we are considering, a comma b.
Origin of the unit vector. Okay, basically origin of the unit vector. Origin means you are basically saying
zero of the unit
starting
vector.
point of the vector.
Yes.
Like this, right?
Right.
This starting point. That is not, I mean, origin is this one. Yeah, fine. Correct. So yeah, I have posted this link in the chat so you can see it on your own at some point if you want. Okay. So till this point, it is clear what is directional derivative and all this thing. Okay.
Yes.
Yes.
Okay. Great. So now let's jump to the first topic of week 10. So I have basically take the PDF of Solve With Us assignment, which is already in your portal. So the first point which we have came across, basically which was already in week 9, that is gradient vector. Now what is gradient vector? We have taken partial derivative at each point. And if we consider that vector, fx1, fx2 to fxn, that is our gradient vector, right? So can you tell me where this gradient vector will be? I mean, what is the direction of this gradient vector? Any idea?
The perpendicular to the plane of the surface.
Perpendicular, not plane of the surface, perpendicular to the tangent plane at that point, right? So if I show it, yeah, somewhere it is there. Suppose this is your surface. I mean, this is your function, this one, the surface. So your tangent plane will look like this. How to find tangent plane? That is a portion of your week 10. I will come to that later. Maybe not today, in the next class. So this is your tangent plane. The gradient vector will be, see here I have drawn this thing. The black arrow you can see from the origin. Okay, so from the origin, that is your gradient vector. And gradient vector means, suppose we are considering a function fxy is something. So here it is. Let's see what the function is given here. X square by 5 plus y square by 20. This function we have taken. So if we differentiate with respect to x, what we will get? 2x by 5, right? And with respect to y, it is y by 10, correct? And if we consider the point 5, 5, so the gradient vector we are getting, what that is? So my question is, what is the gradient vector of this function at the point 5, 5? Can someone tell me what is that?
Dot
Just calculate it and tell me.
Is it 2x?
What is it coming?
So what is the point?
5, 5. This is the point.
2, 1 by 2?
2, 1 by 2. Basically 2, 0.5, right?
Yeah.
That is the point. So this is the gradient vector. Now we are creating a vector in 3-dimensional, right? So there should be one more coordinate, right? Otherwise we cannot point a vector in 3 dimension. 2, 0.5 will be on xy plane, but we need one more coordinate to fix it in 3 dimension, right? So the last thing which I had taken, that is 2, 0.5, -1. Why this -1 is coming, I will tell later when we will study tangent plane. So if we consider that vector, so this is the vector v, vector c, which is written as 2, 0.5, 1. This vector, okay, so this is basically augmentation of your gradient vector. This vector will be perpendicular to the tangent plane. As you can see, this is a tangent plane, this will be the perpendicular to that plane, right? That's how the geometrical significance of gradient vector we can see. Okay, so here it is written gradient vector normal to plane. This is not exactly the gradient vector. This is means the gradient vector with an extension along z axis, it is -1. Okay, why this -1 is coming, I will explain later. Okay. So the significance of gradient vector is basically, in general, we talk about that if we consider a tangent plane at some point, the gradient vector will be perpendicular to that. Okay, clear? Is it clear till this point?
Yes.
Okay, great. Now, the first question which we are seeing here.
So gradient vector always perpendicular to the
tangent plane.
Tangent plane, always. Sir, always, no?
Yeah, it's always perpendicular. That's how it is defined. So when we will learn about tangent plane, it will be more clear why that is perpendicular. Okay, that's how it is defined basically. Okay, so my point was this portion. So where we are calculating where this directional derivative will be maximum, where this rate of change of the function will be maximum, or where it is minimum. Right. So that is the first question. This is called gradient descent. This portion is called gradient descent. So we have seen that directional derivative at some point is basically gradient vector at some point into the unit vector, right? So this is the dot product of two vector. Now dot product means what? So I am considering in two variable, it can be extended to n variable. That is not an issue. So dot product means, correct?
Yes.
Sir, may I ask one question?
Yeah.
Sir, like from further we would be dealing with this gradient vector, right? So do we have to check at any point that it is continuous or not?
Can you repeat once more?
Sir, we would from now on we would be dealing with this gradient vector. A lot of concepts. So do we have to check whether the gradient vector is continuous or not?
So whenever we are applying this formula, we want to find directional derivative using this formula, then we have to check. Otherwise, we don't have to check. If it is asked that where this directional derivative is maximum, then you don't have to check. That means maximum exists. It is already given. So gradient vector is continuous. That is already given to you.
So how do we check whether the gradient vector is continuous or not?
Each partial derivative should be continuous.
That means that if partial derivative which we are writing, it should bear a limit. It should have a limit.
Not only limit, the limit should be same as the functional value. Right? Continuous means two things. Limit exists and the limit should be equal to the functional value.
Sir, can you please write it and explain it? That we are getting three components in directional derivative. These three components are having a limit.
Everything, I mean.
It means that these three limits should be same and they should be equal to the functional value at that point.
No. Fx and fy both are different functions, right? Of xy.
Yes, sir.
Those functions at the point a comma b should be continuous. So fx is a function. Fx will be some function on xy, right? This should be continuous at a comma b. Similarly, fy is also another function of xy. This should be continuous at a comma b.
Sir, suppose just a while ago we calculated the directional derivative of some function like.
I am giving you a function. Okay. Take an easy function. Okay. This one. So yes, what does mean gradient is continuous? So what is fx?
So gradient of this function with respect to x is 2x.
No, partial derivative is 2x and partial derivative with respect to y is 2y. So gradient vector is
2x comma 2y.
Yes. So gradient vector, when we talk about gradient vector, we should define a point. So suppose I am doing at point 2, 5. Okay. So it is 4,
Sir, wait. This you have written this 2x comma 2y. So do we have to check whether this 2x and 2y are continuous?
Exactly. These two are continuous or not.
It means that these two should have a limit.
What is meant by continuity?
The limit should be equal to the function value.
Huh. So first of all, it should have a limit at the point 2 comma 5. Does it have a limit?
Does
Does it exist?
Yes, sir.
Yes, sir.
What is the limit?
2 square plus 5 square.
No, this limit, fx.
4.
What is this? This is 2x, right?
4.
4, sir. 4.
4. And it is same as fx 2 comma 5, correct? So fx is continuous. Clear? And what is this one? Fy?
10.
It is 10. So it is fy. So it is continuous. Clear? If one of these is not continuous, then you can say gradient vector is not continuous. Okay? Clear?
Okay, we have to check for individual component.
Exactly.
For individual component, the limit value should be equal to the function value.
Exactly.
Now I got it.
Clear?
Yeah.
Okay, great. First of all, limit should exist, and then if limit exists, then whether it is equal to the function value or not. Okay? Fine? Clear, no?
Yes, sir, absolutely clear.
The last bit when you said functional value or not means like how substituting the value is what you're referring to directly.
Yeah, right. That is the functional value. Yeah.
F of x means partial derivative with respect to x-axis.
So in one variable, it was also same, right? Limit of fx at this exists. This was the definition of continuity, no? And this should be equal to fa. Right? Similar thing we are doing here. So multivariable limit this exists. This is the first step, and second step is this limit. This was also in week 9. Okay. So this is the definition of continuity. Yeah.
Yes, sir.
Clear, no? Should we go ahead? Okay. Fine. So yeah, what I was talking about. So what cos theta? What is theta? Theta is basically, so this is a vector. U is also a vector. The angle between. Now, what is the maximum value of this theta? I mean cos theta. What is the maximum value?
1.
1, right?
Cos, yeah.
So the maximum, if I want this to be maximum, these are all positive, right? These two are positive. So this must be maximum at least. So this should be 1. And for minimum, this should be -1. That we know. So for 1 is maximum, -1 is minimum. That we already know. And when these two product will be, so now it became product of two things. Suppose this is some x, this is some y, right? Product of two things. Now when this product will be maximum, when x and x into y will be maximum,
when cos theta is equal to 1.
When x equal to y. Basically, I am asking, suppose you have this thing, x is less than 5 and y is less than. Both of them are coming from 1 to 5. Suppose this is my domain. Now, when this, we have a rectangle of length x and breadth 1, y. When the area is maximum, the area is
Five
maximum
y
when
is
both x and y are equal to
5.
equal. Equal and both of them are 5 basically. Correct? That is the case. So for particular x and y, it is maximum when x and y are equal. So this unit vector, that should be same as the gradient vector, normalized gradient vector maybe, because this should be unit vector, so it should be normalized unit vector, normalized gradient vector. So eventually what I am getting, so this is what I was writing, norm of this FAB, and this unit vector is also should be gradient vector, and in normalized form, right? So this is unit vector, so this means 1 anyway, this norm is 1. So the maximum value is this, and so this was cos theta. So when it is 1, this is my maximum value, this is max. And what about the minimum one? We have already
And
seen
cos theta is equal to pi.
cos theta equal to -1, right?
Yeah.
So minimum value is this again.
That's how we are getting plus and minus signs here.
So this is already 1, we know, and this should be -1. So this is minus of norm of this, right? Okay. And what is another thing? This u should be same as grad of FAB. This vector should be in the same direction. And so u is same as this. And as u is a unit vector, so u should be this. So along this direction, it is maximum. And along this minus of this, in the opposite direction, this is minimum. Now you can check again. So if I write dfab along this direction, this vector, so this is grad of fab dot u. Now grad of fab dot grad of fab by norm of grad of fab. Now this below, that is a constant, right? So it will come outside. And here we got FAB dot FAB. So what does it mean? This is norm square, right? This is norm square, correct? And it cancel out because it is positive and non-zero maybe. So this is the maximum value, right? And that we already got earlier. Yeah, this is the maximum, correct? Similarly, minimum you can calculate, just minus sign will be there, correct? So this portion is clear?
Yes.
This is called gradient descent. Okay, so yeah. So basically that is what is written here for multivariable, for n variable. So what I have done for 2 variable, it is written here for n variable. So I think the problems in this section you can do easily, right?
I have one doubt in the example which sir did in the lecture.
Okay.
Sir took a function f of x, y, z equal to x square plus y square plus z square. And he asked
it. 1 minute, let me write it. Well,
So f of xyz is equal to x square plus y square plus z square. Sir, he asked, in which direction does the function remains constant?
Okay.
Sir, I don't know how to get the direction, or he calculated the perpendicular vector. How was that done, sir? There's some
So
confusion there.
in which direction function remain constant mean what? The rate of change of function is basically 0, right?
Yes.
That direction function is constant, right? So basically, you have to find in which direction the directional derivative is basically 0. That is your question. Okay? Can you understand the question? I mean,
Sir,
in
actually,
which direction?
Yeah, sir, because the either it is neither ascending or not descending. The ascent, neither it is ascent nor descent. But how do we get that vector, sir?
No, that is what sir has done in the lecture, you have said, right? Can you tell me how it is done?
So, so professor leave it on okay, how to find that?
No, he calculated some basis and all that. He calculated, but I am not able to understand, sir. How are we getting it?
Okay, so can someone try this? I mean, have you understand the question? First of all, along which direction the function of the rate of change of the function is basically 0. That is the question, right? So along which direction the directional derivative will be 0.
We have to find u, I suppose.
You have to find orthogonal vector.
We have to find u at which this f is 0.
So directional derivative, this, right?
2x.
So this is basically grad of this dot u. You have to find u. You don't know u. And this should be 0, right? So basically you have to find u such that it is orthogonal to gradient vector, correct?
Yes.
That is your question. Now what is your gradient vector?
Sir, it would be 2x, 2y,
2z.
2z.
Now, if some particular point is given, can you find a vector which is perpendicular to this? I mean, orthogonal to this?
Yes, sir. The dot product should be 0 because.
Right? Yeah. So that is your question basically. So suppose I am giving you a point 1, 2, 5. Okay. So what is your gradient vector?
2, 4, 10.
So now we have to find u1, u2, u3 such that this is 0, correct?
Sir, it could be 1, 2, 0.
Is it? Why?
Sir, 2 into
what
1
is it coming? 2u1 plus 4u2 plus 10u3
yeah,
equal to
it's
0.
not, sir. It's not 0.
So basically, all such vectors
it could be
such that this condition is satisfied. So I can simplify it little bit, I think. 2 can be taken common. So basically u1 plus 2u2 plus 5u3 equal to 0, right?
Okay, sir, it could be 2, minus 4, minus 1, 0. 2,
there are infinitely many vectors. This is the subspace we are talking about. Any vector in this subspace will do the job. Okay? Along any vector which is inside this subspace, the rate of change of the function.
Okay, sir. 0. Now we have got a basis sort of thing.
Exactly. So this is your subspace, right? So you can calculate the basis of it, right? Can you tell me a basis that I have taken in live session, this type of thing.
Yeah, sir.
Can you give me a basis
First,
of W?
first, yeah. U1 is equal to 1, U2, U3 is 0. Can we take like
Huh?
that?
Uh-huh.
1, 1, 0, 0.
Is it? If U1 is 1 and U2
Yeah.
is 0, can U3 be 0? Then it is not satisfied, no?
Yeah, that is not. Yes. So UT is
So basically, this
It
means
should be
what?
minus
U1 plus
1 by 5,
2.
sir. Then it will get satisfied.
yeah.
Ah, exactly. U3 is minus 1 by 5. And another one?
Another
Now this is
0,
0.
0,
This
2,
is U2, you can take 1,
1.
right? And what should be your U3?
Plus 2 by 5.
Exactly. So this is the basis of W. This is a two-dimensional vector space, and this is one basis of W. You can create a infinitely many basis, but this is one basis of W. Clear? So yeah, this is very good problem. This is a really good problem, and thanks for asking this. Okay. So is it clear at least now?
Yes, yes.
Sir,
Yes.
Yeah.
sir, earlier you had found the formula for U as the gradient upon the norm of the gradient. I didn't understand how we arrived at.
Which one? Which one? This one?
No, earlier.
No, directional derivative means gradient dot u, right? Some unit vector, right?
No, this I've understood this question. Earlier you had found the formula for U as I think gradient divided by the norm of gradient. I didn't understand
So
how we arrived at this.
okay, fine. Sorry. Okay, so basically we are trying to find when directional derivative is maximum.
Yeah, this I understood how when directional derivative will be maximum and when directional derivative will be minimum. Till here I've understood. But
Okay,
I didn't
then
understand the derivation of U.
oh okay. So eventually what we got? We got two things, right? This grad of f comma ab and u, product of these two, right?
Yes, but U is
Huh.
1.
U is 1. So this is 1 and this is 1. So this is the maximum value, the norm of grad of a comma b, right? This is the maximum value and
Yes,
this is the minimum
yes,
value that you have understood, right? Now,
yes.
what is the option for this one, this radio, this u vector, when it will come as norm of this? That is the question, right?
When it will come as 1.
Norm of a comma b. What is the choice for you for which it will come as norm of a comma b, right?
And
No, this is the maximum value, right?
yes,
So now what is your choice? So this is your directional derivative. This, this is basically grad of f(a)b dot u. Now what is your choice of u for which when you calculate it will come as norm of a comma b, right? So let me write it clearly here. This is in general, right? Now maximum value of d of f(a)b is basically norm of grad
the
f(a)b.
gradient.
Till that portion you have understood, right?
Yes,
Now grad of ab dot u should be norm of ab. What
yes,
should be the
yes.
value of u here? This is the
The
equation,
norm
right? This
divided
is
by
the
the gradient.
exactly. So that is only one option, right? Because if we take the scalar product with the grad, then it will become norm square. And that's what we want. And this should be the unit vector. So we have to normalize it. So the choice for you is nothing but grad of FAB by norm of FAB. Correct?
So you're saying this u when we I mean if we take this gradient on the other side, we'll find the value of u, but we still have to normalize it. Okay, we have not
We are not
normalized it.
taking this on the other side because this is dot product. We cannot take like that.
Oh, okay, yeah, it's dot product.
This is not
Yeah,
product, right? We
yeah,
cannot take it on
yeah,
the
it's
other
a
side.
dot product. Yeah, yeah.
So basically we have to
So
see what is the choice we have for you. The choice we have for you is basically grad of a comma b, and now this is a unit vector, so we have to normalize it. Then we get this thing. Okay?
yeah,
Clear, no?
yeah, I think I need to work through this again. I have understood that it's a dot product and we have to arrive at that.
Right. Okay, fine. Yeah. Okay, so this is what. And remember, in this case, theta we have already derived, right? Cos theta is 1 for maximum.
Yes, yes.
That means theta is basically pi by 2. Right? Okay. So this portion we have done. Any other doubt in this section? This gradient descent? Any doubt you can ask here? No? Okay. Fine. Now, so then we go to tangent. Okay. Tangent line and tangent plane. So, if we consider this surface of a multivariate function, suppose at this point we want to find the tangent line. So, is there any unique tangent line for this at this point? So, in one variable, when we are talking about one variable function like this, suppose we want to find a tangent line at this point, there is a unique tangent line, right? Like this. But for this point, there can be infinitely many tangent line, right? Is this clear?
Yep.
Yes, sir.
But all of this will lie on a particular plane. That is called tangent plane, which consists all the tangent line. Right. So if we want to find a particular tangent line, then we should mention along which direction we are talking about. Along a particular direction, along a particular vector, we can find a particular tangent line. That we can do. Right? So that's why this thing here is coming. Now again, we are considering a function in two variable. So on a domain containing some open ball around a comma b, that's all you have already seen. Now equation of tangent line of a function at a point a comma b in the direction of unit vector, this part is important. Otherwise, we cannot find any particular tangent line. Now there are three type of form which we will study. One is parametric form, one is symmetric form, another is vector form. Okay. So basically, let's start with parametric form. Parametric form means there is one parameter. If we change the parameter, the different value we will get. So what I am trying to say, let's write it here. So tangent line. So fxy is our function. AB is the point at which we are trying to find the tangent line. And the vector we are considering u1, u2. Along this unit vector, we will find the tangent line. Okay. So the equation of a straight line in 3 dimension, we are writing the equation. So we are writing it as tu1 yt as tu2 and zt as f of a comma b plus t what is that u1 u2, right? Z is given as how it is written tfu ab. So what does it mean? This is the parametric form. So here t is the parameter. T is called the parameter. So it depends on one parameter, and we are getting three things. X is depending on t, y is depending on t, and z is also depending on t. Now you can see that the z value, the z coordinate, it depends on the directional derivative of a comma b of the function f at the point a comma b along the direction u. Okay, so that's how it is written. Now everything what we are getting here is basically, if we see t x minus a by u1, and if we consider here t is basically y minus b by u2, and from the third one we are getting this. Okay, now all of these are t, so we can equate these three. So this is basically equation of a straight line in 3 dimension. Okay, so first of all, tell me, if I consider a straight line in 3 dimension which is passing through origin, that is a vector subspace, right? What is the dimension of the subspace? Can someone tell me what is the dimension of the subspace?
Three.
Huh?
So 3-dimension.
Three.
Y, Z, X and Y along the Z axis.
Have
It's
you
2
understood
dimensions,
my
isn't it?
question?
It's
What
in a
I
plane.
2 dimension, is it? My question is, in R3, what is the dimension of a straight line passing through origin?
Three. Two.
X comma minus
Two,
X
sir.
comma Z. So it's
Two, sir.
2.
Is it? It's 1 basically. So in R3, how many types of subspaces are there? 4 type, right? One is 0 dimension, that is only origin. 0, 0, 0. Then straight line passing through origin.
Yes, one.
This
One.
is dimension 1.
Plane is 2.
Then plane is 2 dimensional,
Plane
right?
is 2. Correct.
2 and then
R3
the
itself.
whole R3. This is dimension 3, right? These 4 type of subspaces are possible, right?
Yes, yes.
Okay, fine. Now, if I want to write this straight line, okay, so this is inside R3, so x, y, z, and some constant will be there, right? How many constant we need? How many condition do we need? two condition we need, because the dimension is 1. So this x, there should be some dependency on x and y, there should be some dependency on x and z also, right?
Yes.
So if I want to write any equation of a straight line in R3, this type of situation must arise. Two condition. So first condition is basically this one. The second condition is basically this and this one. First and three. So obviously these two are connected, right? So two constants should be needed, right? If I want to write a equation in a equation of straight line in R3. If I want to write a equation of a plane in R3, how many condition is needed? One. Right? Is it clear?
Yes, sir.
Is it clear to everyone? If you have doubt, you can ask me. I understand.
Yeah.
The last part.
Can you explain that?
Okay. Basically, I am trying to connect the linear algebra portion with this. So that's
Yes,
what
sir.
I
Yes,
am
sir.
trying to do. So basically, if I am saying, if two conditions are given, f1 xyz is 0 and f2 xyz is 0, two independent conditions are given. These are constant. So suppose xyz is x equal to 4y, right? X equal to 5z. If I write like this, so this is x minus 4y equal to 0, this is x minus 5z equal to 0, right? So if I write this, what will be the dimension of this subspace?
1.
1. So basically this is x, this is x by 4, this is x by 5.
Yes, sir.
So only x is our independent variable. So dimension of w is, so this is my w. So dimension of w is 1, correct? Because I can write a basis of w like 1, 1 by 4, 1 by 5. So this will span the subspace W, right? So this will be a straight line. This is a one-dimensional subspace in R3, and one-dimensional subspace in R3 means this is a straight line passing through origin, correct?
Yes.
Till this portion it is clear. So two constant is needed. Now, if I want to write the equation of a plane, I said one constant is enough. So suppose this. Forget it. Suppose I don't need this x plus 2y equal to 0. This is only one constant is given, right? So if I write it, this is w prime, say. Now this will be a plane, right? We have already seen y equal to mx will be a plane in R3, right? When we are talking about limit today. In GeoGebra, we have shown it. So this is x, this is minus x by 2, this is z. So two variables are there, x and z, two free variables are there, right? So dimension of w prime is 2. So this is a plane, correct? So this is a plane. This is a straight line. Clear?
Yes.
So if I want to write equation of a straight line, I need this type of situation. So this is eventually this we can write it as x equal to 4y equal to 5z, like this type of equation is needed. So exactly this type of equation we are getting for a tangent line. Now the problem is tangent line is not passing through origin. It may or may not be, but this is not a subspace. This is what it is called, affine subspace, right? We have seen it in week 8 or 7 maybe. 7, right? So this is affine subspace or affine straight line. Okay? So affine subspace is basically a better term for this. Let it be there. And the dimension of the affine subspace is same as the dimension of the subspace. So dimension is 1. Clear? So this is the equation of a straight line which is passing through the point a comma b comma f of a comma b. Because we are trying to find a tangent at this point at a comma b. So at a comma b means what? So if my point is here, if a comma b is here, So here the point is, on this surface it is a comma b comma f of a comma b, right? This is the point here. So the tangent line which we are considering, this should pass through this a comma b comma f of ab. So
Yes.
this is the equation of a straight line which pass through passing through a comma b comma f a comma b, and the vector we are considering here u1 u2, right? So suppose u1 u2 is here, so we transident here u1 u2, and what we will do, we will see the directional derivative along this direction, right? We have seen how directional derivative is considered here. So along this direction we will calculate the directional derivative, that will be f of. So the equation of straight line in 3 dimension, who have already studied 3D geometry somewhere in your course, not in this course, in some of your course in your earlier life. So you have seen that these are called basically direction cosines. That is not important. The term is not important here, but I am mentioning these are basically direction cosines. So basically, if the equation of a straight line passing through this point will be x minus a, y minus b, z minus c, suppose it is passing through a comma b comma c, and below there should be direction cosine. That is, so here it is u1 u2 and directional derivative of along the vector u at the point a comma b. So that is the equation of tangent we are getting here, right? And now if we want to parameterize it, we should equate it to t, and we will get back to this parametric form. Okay, so t is the parameter. Okay.
But sir,
Yeah.
why we divide direct at the unit vector u1 u2, sir? B should multiply now. If we want to tangent along that unit vector, we should multiply that unit vector,
Why we should multiply?
because we are taking in that direction along unit vector.
Then why
Suppose
it should be multiplied?
suppose suppose sir, suppose we want to go like a vector with unit vector u. So a dot u, a dot u, we always mention.
No, that is for plane. When we are considering the plane along that, that
Yeah.
will be the, then we should multiply that. That
Okay.
is the equation of tangent plane. But when we are
Okay.
considering equation of a tangent line, we should
Yeah.
divide with the direction cosines, the direction we are talking about. So in that case,
Okay.
we have to multiply, divide
Okay.
it.
That's why divide. Okay.
Yeah,
Right.
right. Yeah. So here we don't need all this theory behind why we are considering this equation, but at least you have an idea conceptually or geometrically that that's how these two equations are coming. One is symmetric, this is symmetric form, and that was in parametric form. So let me summarize it once at the end. So what I am saying, fxy is our function, given function. At a comma b, we have to find the tangent along the direction of the vector u. Okay, so what will be that? It is x minus a. So there should be the tangent line should pass through a comma b comma f of a comma b, right? This is the first condition. This should pass through this, and the direction should be u1 u2 fu a comma b, correct? So how we write the equation? X minus a by u1, y minus b by u2, z minus f a comma b by f u a comma b. Okay, fine. Is it clear?
Yes.
Okay, fine.
So this is the equation of the tangent.
Tangent line. This is the equation of the tangent line. So this is called the symmetric form. Now,
That means if you want the equation of the tangent line, we can just simply do x minus a upon u1.
exactly. This is the formula for
Or
that.
either of them.
Now this is symmetric form. Now if we want to go to the parametric form, what we will do, we have to take this as some constant. So all these are equal. So we take a parameter. This is called a parameter t. So what is the x? Now x is basically tu1 plus a. So a plus
tu1.
tu1. So now it depends on t. That's why we write xt. Similarly, yt is b plus tu2 and zt is tfua comma b. So this is called parametric form. Okay, clear? So whatever form you are asked, you can answer from here. So and another is called vector form. So this is exactly writing xt, yt, and zt in this form, basically, right? In forms of a vector. Okay. So let me write how vector form will come. So basically you are writing xt, yt, zt. So what is this? This is a plus tu1, comma b plus tu2, comma fab plus tfuab. Now using the property of vector addition, we can separate these two, right? Sorry. Correct? We can write it. Coordinate wise addition, if we do, then we will get back to the second step. And now we can take this constant outside, right? This parameter outside. Clear? So that's how we get the vector form. Okay. So if you just remember the first symmetric form, then I think everything you can just derive. You don't have to remember all the formulas. You can just derive it in the exam hall itself. It will not take much time. Okay? Clear?
Yes, sir.
Okay, great. Okay, so we can see that, okay, so let me do tangent plane first and then come to this. And what about tangent plane? Tangent plane is basically the plane which contains all the tangent lines along any direction. If you take tangent, if you consider all set of all the tangent along any direction, and that all will lie on a plane, and that is your tangent plane. Now, what is the equation of tangent plane? It is basically like this. Equation of tangent plane. So should we do? Fx a comma b x minus a right? Correct? This is what we need. This is the equation of the tangent plane. Or you can write this on the other side. That depends on choice. Z minus f of ab. Okay. So basically tangent plane also should pass from these points, right? So A, B, and suppose this is C. What is F, A, comma B? So tangent plane should pass through these three, these point, and it will be the equation of plane. So it is should be two-dimensional. So that's how the equation of the tangent plane will come like this. Okay, and this fx and fy, this comes from the Gaussian vector, as you can see. This is the part of the Gaussian vector. So here it is written like this. So the same thing what we have written, that is here. So my point is, yeah.
Sir, fx and fy is partial derivative, sir. Okay,
fx and fy
yeah.
is the partial derivative. Exactly. Okay. Yeah. So basically what it's happening here, it is z minus fab equal to Gaussian vector if at the point AB dot x minus a y minus b. This is the thing of the tangent plane, right? If we expand it, we will get back here. Okay, so this form is basically good when we are talking about n variable thing, because then we can just write it in a, I mean, simple way using this form. Okay. So if we consider this, if we break it down a little bit, so this is the coefficient of x, this is the coefficient of y, minus z, we take all the constant on the other side. So equals a fx ab b fy ab minus f of ab, right? This is the plane we are talking about, right? This is the tangent plane. Some constant. So you know any plane in R3 will look like ax plus by plus cz equal to some constant d. So here your a is this, your b is this, c is minus 1, and d is this constant, this whole constant. Correct? So earlier I was saying the Gaussian vector, the third component I will add minus 1 so that it will be perpendicular to the tangent plane, right? Now can you see the reason why the third component was minus 1? This is the reason.
Yes, sir.
Correct? This is the first component, second component, and this is the third component, because the coefficient of z is basically minus 1. So if we consider this plane, right? If we consider the vector a, b, c, this vector will be perpendicular to this plane. Okay? You can check. This vector will always be the perpendicular to this plane. So here, this is nothing but the Gaussian vector fx ab, fy ab, and third component is minus 1. So this vector will be perpendicular to the tangent plane. Clear?
Yes, sir.
Okay, great. So now if we go back to GeoGebra, this is exactly what we have done here. So at some point, so this was our function. At 5 comma 5, we are calculating this. So basically, the point is 5 comma 5 comma f of 5 comma 5, that is 6.25. They have calculated, and the vector is taken as 006.25. That is the vector. So they have calculated all this thing, and the plane eventually they got is like this. Okay, the plane which is saying, so this is that equation of the tangent plane we are getting, and the vector which I have shown below here, this vector, this is basically the gradient vector which is perpendicular to the tangent plane. Okay.
What is black line, sir? A long black line.
So you can see the gradient vector and this black line is basically parallel to each other, correct?
Okay.
So that line is called normal to the plane, normal line. We don't need normal in this course, but still it is better to know what is the normal. Okay. So I will show you another picture here. This is a better picture for this. This. So forget this one. X square plus y square is our function. So this is how it look like.
Yeah.
And we take the point 1 comma 1. Okay.
Yeah.
So here.
Purple dot. Yes.
Now if we consider tangent plane, it will look like this. This is the tangent plane. Now normal line which I was saying, which is perpendicular to this, normal at this point, basically perpendicular to the plane at that point. Okay, that is the normal line. So you can see the normal line. This is the equation of the line we are talking about using a parameter we are doing, and this vector -2 comma -2 comma 1, basically this is your gradient, the gradient vector we are talking about. Okay, along with -1 at the third coordinate. Okay, fine.
Yes, sir. Yes.
Okay, great.
So, sir, here P is the point 112.
Point was 1 basically point was 1 comma 1. Now if we put 1 comma 1 here, we will get 2. So that is our point. Okay. Okay.
I said, could you share the link of this also as you shared the link earlier?
I will send. Okay, let me share here itself. But I will send a mail with all this link. Okay, to all of you.
That will be good.
Because you need this to visualize.
Yes.
Otherwise, everything in week 9 and 10 is basically formula manipulating and everything. But you have to visualize what is going beyond that. So that's why I am trying to draw today.
So even I did not know how to get the one Geogebra. We tried, but we could not find how to get
That
Okay,
is a
so
processing itself.
Geogebra.
okay,
This is
so basically
easy.
these are inbuilt. What I am sending to these are all inbuilt except this one. This one I have created myself. So here we can see how the programming is written. Okay, this is what I have created. You can use that also. So I will send it. You see, this is one small portion, but at least you can try your hands on this. Okay, then we can
Yes.
discuss more in detail later. Okay, so can we stop at this place, because otherwise it will be again. So we have reached till tangent plane and tangent line, and one more topic is remaining, that is critical point. So other than that, in week 10 everything is done. So in next session we will start from critical point. Will that be okay?
Yes, sir. But
Yes, sir.
are you going to take the next session, sir?
Same question.
When is the next session? It is Thursday, is it?
Thursday, yes.
No, I think it's
I will
Friday.
take.
I think it's Friday.
Okay, Friday I will take.
Friday only.
The continuation will be better.
I will take the next session. No issue.
Yes, sir.
Sir,
Thank you.
sir, in one of the
Yeah.
videos, I think this second or third video this week, sir talked
Mhm.
something about affine flats, and I don't think I've come across that term.
Affine flat means affine subspace, and flat means basically affine plane. Okay, those are called affine flat. So plane is a two-dimensional subspace of plane passing through origin is a two-dimensional subspace of R3, right?
Yes.
Now, if we transcend
Trans
that along
yeah.
z axis or along any parallelly, basically, so whatever we
Yeah.
get, that is basically affine flat. So all the
An
tangent
affine
plane are
flat.
basically affine
Okay.
flat. Okay, so basically, yeah, any tangent line will look like this, right? Ax plus by plus c is equal to d, where a, b, c, d like this, correct? So our tangent, this is when this is 0, this is the subspace, correct? This is two-dimensional subspace.
Yes.
Dimensional subspace. Now, our tangent plane will be like this, d. Some constant will be there. This d may not be 0. May be 0, may not be 0.
Yes. Yes.
So it will be a affine subspace. Okay, that is the connection. And this is called affine flat. Because this is a plane, that's
When
why
D
it's
is
called
not
flat.
zero.
Even if d is 0, any subspace is also a affine subspace. Any vector subspace is also a affine subspace, but all affine subspaces are not vector subspaces. Correct?
Yes.
Okay. Any subspace, any vector subspace is already a affine subspace, but there are more. I mean, affine subspace may not contain 0. That is the point. Okay. Clear?
Yes, sir. Thank
Okay.
Sir,
So
I
I will
hope
suggest
you'll be
you.
sharing this. You'll be
I will
sharing
share.
this
Hmm.
notes, please.
Yeah, yeah, definitely.
Sir, hello, sir.
So one thing I will suggest before next session, can you just take a look at affine subspace?
Okay.
So I
Sure,
know
sir.
you have already done, you have already given quizzes, but that one is an important topic. That's why I want to say affine subspace.
Yes, sir.
Live sessions were there, right,
Yes, sir.
on
Yes,
this
sir.
topic.
Yes, sir.
So I want all of you to go to affine subspace. We will discuss about it in next session also. Because any tangent plane or any tangent line, that is not a vector subspace, that is affine subspace. And that's where the connection lies. Okay. So it's
Can you
better
share?
to take a revision
Sir,
there.
because zero origin will be not present there.
May not be there.
May not be there. Yeah.
May not be there. That's why
Sir,
everything. Yeah.
can you share a link to your previous YouTube videos regarding this affine subspaces, last term's YouTube videos?
Last term's video, no? Okay, I will take a look where that is. Yeah,
I
I
searched,
will
but I
share.
could not find it.
Okay. Yeah, there are so many videos in the channel now.
Yes.
So,
But sir,
okay,
it is
I will take a
already
look.
in separated into a playlist. So if we can go through the week 8 session, we will find it.
Yeah. But
The weeks are
somewhere
jumbled.
I forgot in
Previous
which
term,
term I have taken a complete session on affine subspace.
Sir, in the previous one,
I will,
January term.
in the previous one, January
Yeah.
term,
Yeah.
in this term, no, sir.
I forgot that. So I will take a look. I remember that I have taken a
Yes, sir, you
session
have taken a
completely on
full
affine
session
subspace.
only as a fine subspace.
In this
So
term, he has not
No,
taken.
sir.
No, the
no,
previous
not
one.
in this term, in previous
Yeah,
term.
not in this term.
Okay.
Yeah.
Because
If it
because
is
I was not confident, so I went and watched that particular video. So
Can you
Can you?
share the link?
yeah, I will. I will.
Okay, you can share the link. Then you can share it in discourse. Okay.
Okay,
Yes.
sure, sir. Sure, sir. I will.
Okay.
Thank you.
Was it helpful? Was the session helpful on
Yeah,
affine
very
subspace?
helpful. Very helpful, sir.
Okay, fine. Your doubts are clear, right?
Yeah, yeah, yeah.
Yeah. Okay.
I
Yeah.
have a doubt which is even more fundamental. Maybe at the end of the session, if you have a couple of minutes, I'll ask.
Yeah, go ahead. Basically, we'll stop here today. So, yeah.
Okay. Okay. It was with the earlier point you mentioned in R3, a line is having dimension 1. Let's say when you said y is equal to x, then we are actually talking about x and x comma minus x, but z is also there in R3, isn't it?
So y equal to x is not a line in R3. So
Y is equal
that's
to
why
x is a
I have
plane.
shown in GeoGebra, no?
Yeah.
So suppose, yeah, this y equal to mx I have taken,
Yeah.
right? So if
Yeah.
you put m equal to 1, so let go here. So it's difficult to, so 0.9 maybe. So this is a plane, right? This is not a straight line. So
Yeah.
this y equal to mx, y equal to x maybe, where it intersect with the xy plane, that is your straight line y equal to x, right?
Correct.
In 2D.
Yep.
But now when I am talking about this y equal to mx in R3, that is not a straight line, that is a plane, that is two-dimensional thing.
So
because if we write it, what is it? Y equal to mx in R3. Right? We are talking about this.
Correct.
So this means what? This means x, mx, and z is there.
Yep.
So there are two free variables. Right?
Yeah.
So if you put m equal to 1, then this is your subspace. What is the dimension of this subspace? 2, right?
2. Correct. But yeah, that's what.
If you can give a basis. 1, 1, 0 and 0,
0, 1. Yeah.
Correct? So this is a two now. So this is a plane. This is a plane in R3. So if we have to consider a line in straight line in R3, so first consider a straight line which is passing through origin. It is better to take that because we can talk about a dimension of a subspace in that case. So there should be two constraints, not only one constraint, right?
Yeah.
That's what I have mentioned earlier somewhere here. No? Yeah. X equal to 4y and x equal to 5z. Two constants are there. Now it will become a straight line. Because then our subspace will be x, comma x by 4, comma x by 5. Right?
Yeah.
So only one free variable is there. So this is a dimension 1 subspace. Right? Now if you can move the straight line, you will get a affine straight line or affine subspace. Okay? That is also of dimension 1. Okay.
So when we talk about R3 and straight line, we cannot have a straight line, is it? Or we can forcibly say
this
it
is
is
a
fixed?
straight line. No? This is a straight line. The equation is not like y equal to mx. That's my point.
Yeah. Okay.
The equation will look like this. This.
Yeah.
Two equality will be there.
Okay. Yeah,
like
one
this.
is relating
This
to
is
y,
the
other
this is the
relating to
equation.
z.
This
Okay.
is the equation of a straight line in R3. X equal to 4y equal to 5z. That is the equation. If I only write x equal to 4y, that is a plane.
That's a plane.
Because z is free there, no?
Right. That was my doubt actually.
So you can visualize it. X equal to 4y. So on xy plane, it is just x equal to 4y. Now you take all the z's. So it will become a plane.
Yeah.
That is how you should look at it.
Yeah. Okay. Thank you very much. Yeah. Clear. Much clear. Thank you.
Sir, may I ask a question?
Yeah, sure.
In the tangent plane, it was x. No, it was even in the line. It was xt. What does the t denote?
So this t, right? Well, this one, right?
X
this
bracket t. Yeah.
So basically, first of all, this symmetric form you have understood how it came, more or less. So now all these are equal. Now I am, these are basically ratio, right? X minus a by u1, y minus b by u2. So these are like ratios, where these ratios are same. So I am taking some proportional constant here. That is our
Okay.
parameter t. Okay.
Okay, that is a okay.
That
We've
is our
taken some
t.
constant, some
Some
value
constant.
t.
Now here we don't call it constant because for different value of a, b, and
Will
u1,
change.
u2, it will change. The ratio will change, right?
That's why we're calling it a parameter.
That's why we call it a parameter. Okay, this is not constant. This is parameter because uh, for particular a comma b and u1, u2, it is fixed, but all these a, b, and u1, u2 can vary. Then t will also vary. That's why it is parameter. Okay,
Okay, that's why
and
we're saying
now
x for that particular t.
exactly. So if t changes, then x will also change. So x is a function of t.
Okay.
Okay. When we write f of x, what does it mean? F is a function of x, right?
Yes. Yes.
So similarly here, it depends on t because once we fix a and u1, this will be fixed. Now t is our parameter. T can vary. So we can write x as a function of t.
Okay.
Okay. That's why it is written like this. Okay.
Yeah, this is making a lot of sense. Sir, it's really been nice. I had memorized and understood how to calculate the directional derivative, but that visualization has been very nice. I understand
Yeah,
better.
that is needed, I think. Visualization is needed.
Everything was
Otherwise, there is
abstract
nothing
till
to
now.
do in this week 9-10 other than visualization.
Yeah, it was very difficult to visualize without that particular
Right.
in
Sir,
GeoGebra.
Yeah, correct.
so, hello, sir.
Yeah.
Sir, I have a small doubt regarding differentiability, sir. Can I ask a small question?
Differentiability we have not done yet, no?
No, sir. Sir, actually, I have a doubt regarding differentiability and critical point for one variable, sir.
Oh,
Uh,
okay.
yeah, it is the some like a conceptual doubt, sir. We have, sir, I mentioned that for a critical point, fx may be differentiable or not be differentiable. Some case like that. If for differentiable f dash a is equal to 0, and for differentiable, what should we do, sir? How do we get a
I
critical
got your
point?
question.
Yeah.
Right. So we call a not a comma b. I am writing here. So we call uh, x equal to a as critical point.
Yes.
We call it critical point. So I am talking about one variable, okay? So next
Yeah.
session
One.
we'll talk in multivariable,
Yes.
so then I will
Yes.
change it. So x equal to a is a critical point if either of one condition hold. First is if may not be differentiable at a,
Yes.
then also we call it a critical point. If is
Yes.
not differentiable at
Okay.
a.
That is main.
Uh, and second, if f is differentiable,
Yeah.
at a, then this should hold.
F dash a is equal to 0. Yes.
Right? So this was the definition of critical point.
Yeah.
So one part is there. Yeah, right. You are right, basically. If it's not differentiable at a, then also we call it a critical point.
Yeah.
And if it is differentiable, then this condition should satisfy. F dash s should be 0. Okay. So, I mean, one particular example you can see, if we consider mod x, 0 is a critical point, right?
Yes.
At 0, the function is not differentiable, right?
Yes.
So 0 is a critical point, and you can see that 0 is indeed a minimum because it is the minimum value of the function,
Yes.
right? Yeah, that's why this definition is made. I mean, that is the motivation behind the definition. Okay, got it?
Yes, sir.
Clear, no?
Yeah.
Great. Okay. So today I am ending the session here.
Thank you. Night.
Yeah.
Thank
Good
you.
night.
Thank you, sir.
See you.
Thank you,
in the
sir.
next session. Yeah.
Sir,
Great.
sir, just one doubt.
Uh-huh.
So do we remember all the trigonometric derivatives and logarithmic derivative for this multivariable function?
Log trigonometric derivative means only sine cos, you know, right? Sine cos and
Yeah,
tan.
tan. Yeah.
That is enough. And log 1 by x, log x differentiable 1 by x, that is enough. But we don't need it for multivariable basically. When we are calculating what
Because
is
I
it?
have seen
Partial
some
derivative.
of question in activity or practice.
Some partial derivative, if you have to calculate, you need
Yeah,
that.
that's why I'm asking. Do we need it or?
But it will not be very difficult
Yeah, it's not
for
very difficult.
calculation.
I'm just asking that whether we should remember it or is it okay to?
So I will say for exam, you just remember easy type of thing,
Okay.
and when you will work in real life, you got the data in your hand. You don't have to remember anything, right? You just search in Google, you will get what is the derivative of this. No point in remembering all this.
Yes, sir. Thank you, sir.
Yeah. Okay.
Good night, sir.
Okay. Good night. Good night.
Good night, sir.
Good night. Good night.
Thank you, sir.
Yeah.